All right, so segment 4, we've been talking about oxidation, reduction reactions, kind of introduced you to the activity series, and we're going to pick up from there. So, all right, how does the activity series generated? Well, it came from observation. If we take acid and we react it with strontium metal, then what happens is we end up with a strontium ion and hydrogen gas is observed to come off the reaction. This simply means that H plus then will oxidize the strontium metal to strontium 2 plus. Okay, and that means that the strontium then reduces the hydrogen from H plus to elemental hydrogen, which means its oxidation number is 0. We can also say that the more active strontium then replaces the less active H plus, and so strontium is easier to oxidize. Okay, that's what that's telling us. Now, if we try the reverse reaction, so if we take hydrogen gas and pump it through a solution of strontium 2 plus ion, it actually gives us no reaction. Okay, so why is that? Well, basically, the reason is the hydrogen is less active. Okay, so the hydrogen can't seem to replace the Sr2 plus. And so that means it can't reduce the Sr2 plus to Sr0. All right. Now we can observe a whole series of reactions, and then from that observation of those reactions or lack of reactions, we've been able to develop that activity series. So for instance, if I were to take 3 reactions here and put them together and say, okay, we have copper reacting with HCl, zinc reacting with HCl, and magnesium reacting with HCl. And in one case, we get no reaction whatsoever. And in the other 2 cases, we see hydrogen gas come off of one, and we see zinc solid react and come off the other, right? So based on those reactions and your observations of those reactions, rank the metals from most reactive to least reactive. And so the way we would see this is if I take magnesium metal and I put it in solution with zinc chloride, the magnesium replaces the zinc, gives us magnesium chloride, and we'll see zinc solid appear. If I take zinc solid and I put that in HCl, we'll see ZnCl2 solution. So basically, we'll see that start to disappear. So we'll see the zinc disappear. And what we'll observe is little bubbles appearing on the zinc, and that's going to be our hydrogen gas. And then if I took copper and just threw that into a test tube with some HCl, it just sits there. We'll see no reaction whatsoever. So we'll see no gas bubbles being made. We'll see the copper not deteriorating or changing color or falling apart at all. All right. So based on that reaction set, what we can see is that the magnesium can replace the zinc can replace the hydrogen, the copper replaces nothing. And so the most reactive then would be magnesium, and the least reactive would be the copper. And so our series would look something like that. All right, now reactivity can vary by metal. The metals at the very bottom of our table are very strong reducing agents. They're very easily oxidized, and so sodium down to cesium. So if I look looking down looking down the group on the periodic table, the metals at the very bottom, the reactivity tends to go up. Okay, so alkaline earth metals, we can witness this. We can react them with water as well as just acid. And so if I take sodium and I put that in water, what we get is H2 gas being emitted, and we'll notice that the acidity of the solution becomes basic. So it goes from a neutral solution of water to a basic solution because that's sodium hydroxide being formed. And of course, if I move down the periodic table, the different metals, they become more and more reactive with water. Okay, so that reaction becomes more and more violent, which means it's more reactive. So reactivity varies by metal. If I take different metals and I put it in HCl, then of course we can see different things. For instance, if I take silver and I put that in HCl, no reaction really takes place. Okay, so the HCl plus the silver solid very slowly, very quietly gives us H2 gas. If I take iron, now we're going to move across from the periodic table, right? And I put that in, again, very little reactivity. They give you a picture of it here. You can see there's the chunk of iron in there. You don't see any bubbles really in here at all. There might be 1 or 2 forming on the metal itself, just not very reactive. Okay, but slowly but surely we're making hydrogen gas. Now if I throw a piece of zinc in, we call that somewhat reactive, and now you can see the bubbles all coming through the test tube here. All right, so we get the middle of the activity series, we get 2HCl plus zinc is going to give us zinc chloride, and now we can see that hydrogen gas forming. And then last but not least, if I take a chunk of magnesium and I throw it in, you can barely see that's the magnesium right there. Right? You can barely see it over top of all of the bubbles that are being formed from the hydrogen gas that's evolving off of the reaction. So here we have HCl plus Mg gives us magnesium chloride and hydrogen gas. All right, so we can use the activity series then to predict reactions. So if the metal that is below reacts, so if you have hydrogen sort of in the middle of the table, if the metal is below it, then it can displace the hydrogen and forms the solutions containing H+, right? So 2H+ would then go to H gas, H2 gas. If the metal is above the hydrogen, then it won't react. Okay, so it won't react with any of our non-oxidizing acids, so the HCl, H3PO4, etc. Now, in general, the metal below replaces the ion above. Okay. Now, again, you got to be careful which activity series you're looking at. If I were to go out to Google and then do Google images on reactivity series, sometimes we'll see magnesium at the top and sometimes we'll see magnesium at the bottom. What you would do is pay attention to that. Magnesium is going to be one of our most reactive metals. And so it's going to replace most other things. Right? So just keep in mind when you're looking at it in the slides here, they're basing it off the picture we saw in segment 3, which, if you recall there, I even pointed out it was reversed to the ones we usually use in class. All right, so reactivity series then can be a predictive tool to determine the outcomes. If you're given a metal and then the ion of that different metal, you can look at where they are on the chart. On the chart the textbook's providing, if the arrow points up, then that reaction will occur. If it points down, then it will not occur. Okay. So for instance, if I take gold and I react it with calcium, and if I go back and look at their table, then in theory what we should see is gold is above the calcium. And it should make sense. Calcium is a very reactive metal. It's probably very close to the bottom of our table, the way they've got it drawn in their textbook. And so it's going to be pointing up. And so that means the reaction should take place. Now if I reverse that and I take the metal and the calcium ion, now my arrow would be pointing down, and so we're saying that's going to be no reaction. Okay, and so again, if I take tin and sodium, tin should be above, sodium would be quite towards the bottom. Again, the arrow is pointing down, and so we'll get no reaction. If I take manganese and cobalt, here now you can see that that arrow should be pointing up, and so we'll get the reaction of cobalt solid and manganese ion. Last but not least, again, if we take copper and we see that it reacts with H+, the arrow is pointing just slightly down, but still down nonetheless, and so that's going to be no reaction. All right, so let's do some practice problems here with your turn. The activity series of metals is this. And again, a lot of times what I like to do is find magnesium. Magnesium is a very common one. I know that's going to be on the active side or the reactive side if you'd like. And then a lot of times we'll look for copper, right? And I picked copper because copper is pretty much a non-reactive metal. It's one of the few precious metals sort of on the cheap end. It doesn't react with much, okay? Now, based on this list, which element listed below would undergo reduction most readily? Now, remember, we want to go from the ion to the metal. Okay, we're going to go from the ion to the metal. So we have silver here. Then we have aluminum up here, then copper, then cadmium, and then zinc. Well, right away, if we're looking for the one that's going to most easily and readily undergo reduction, we know it's got to be one of the extremes, right? So we know it's either going to be silver or aluminum, just because we're good test takers. And so we know it's got to be one end or the other. So now which end will it be? All right, so here we're going to be looking at Al3+ reducing to aluminum versus Ag +1 reducing to Ag. All right, so based on this list, which element listed below would undergo reduction most readily? So again, we'll be going from +1 to the 0 or +3 from the 0. So based on this list, which element listed below would undergo reduction most readily? And so here we're going to say it's aluminum. Okay. All right, next question. The activity series of metals is here. Again, we have copper, we have zinc, and magnesium. Find those two. Will the reactions below occur? So will magnesium solid, which is here, replace the Na+, which is here? And then will the tin, which is here, replace the aluminum, which is up here? So can tin 2+, and the ion here, replace the aluminum? Right? Actually, I guess I should be saying, should the aluminum replace the tin, right? Because it's what's going to happen. This element by itself is going to replace the tin. So can the aluminum replace the tin? And then can the magnesium replace the sodium? And of course, we can't replace the thing above us, but we can replace the thing below us. So in this case, both of them will not occur. One of them will occur. And of course, it's B. The aluminum can replace the tin, but the magnesium cannot replace the sodium. All right. So if the following reaction occurs, predict the products. So magnesium replacing aluminum. And so now we know the things above, they can replace the things below. So we do believe this reaction will occur. Now what will happen? Well, magnesium we know is going to be +2. So let's see, we know it can't be C, we know it can't be A, we know it can't be E, because magnesium has to go to +2. The aluminum has to go to 0. It can't remain a 3+. That gets rid of the D, which means our answer should be B. And of course, we could balance it and finish that off. All right, so reaction of nonmetals with O2. Many nonmetals react directly with O2 to form nonmetal oxides. So for instance, sulfur can react with O2 and it'll form SO2. So for instance, solid sulfur reacts with oxygen gas and it produces SO2 as a gas. Nitrogen can also react with oxygen. And of course, from here, we're going to form various oxides. So there you go, whole list of them. And we'll point out that it can also form dinitrogen oxide, which is N2O. And of course, that's laughing gas. It's also the propellant in whipped cream. Okay, so again, oxygen can react with nitrogen, form a variation of NO compounds, and oxygen can react with sulfur to give us SO2. So oxygen as an oxidizing agent then, typically when that happens, we think of combustion. So usually what we're looking at is taking a hydrocarbon and reacting that with oxygen, O2. We kind of pointed this out already talking about reactions, but here we're going to get a little more in depth. We know that the products will depend on how much O2 is available. So we have different levels of combustion for when it comes for hydrocarbons. First one we'll look at is called complete combustion. This is like our car engine. You have plenty of oxygen out in the atmosphere to react with the gasoline, the hydrocarbon, to give us CO2 and water as our products. Okay, so CO2 and water. So for instance, if you burn natural gas to heat your home, you take methane plus 2 O2s will give you CO2 and a couple of waters. Right? Or as I mentioned, your car, if you burn octane, you'll get 25 oxygens being used, and again, you'll still produce CO2 and water. So whenever we have complete combustion, our products are always going to be CO2 and water. All right, so oxidation of organic compounds then. Another possibility would be incomplete combustion, and so here we don't have enough O2. So in complete combustion, we have plenty of O2, and in incomplete combustion, we've pulled back on some of the O2. We've limited that supply, and now one of our products is going to be carbon monoxide. So whenever we have complete combustion, we have CO2 and water. Whenever we have incomplete combustion, we're getting CO and water. Now you can restrict the oxygen even more, right? So if I get to a very limited O2 supply, then I can actually make carbon soot, right? So it'd be a solid carbon material. So this is the tiny black particles, like if you've ever burned in a wood stove and you want to maximize the BTUs, you'll cut down on the oxygen to help the wood burn a little longer, then you're going to produce more soot, right? All right. So combustions of organics containing oxygen. So again, we don't just burn hydrocarbons, we can burn hydrocarbons that have oxygen in them, like sugars, things of that nature, alcohols. These still produce CO2 and water, so they still have the variations of complete combustion and incomplete combustion. It's just that now we need less oxygen to actually have complete combustion, right? That's because some of the oxygen is going to be released as we burn that sugar or as we burn that alcohol or whatever that oxygen containing hydrocarbon is. We can also burn organics containing sulfurs in them, so like mercaptans. When that happens, we're going to be producing SO2 along with our CO2 in our water. So you'll still get your two products, CO2 and H2O. It's just now we're also going to get some SO2 in the mix there. Now, here's where air pollution really comes in the forms of acid rain. Okay, so when we produce SO2, what's going to happen is the SO2 can then oxidize to get SO3, and then from SO3, it mixes with water to form H2SO4, which we know as sulfuric acid and is one of our strong acids. Okay. Now we can also have non-combustion reactions of O2. So reactions with O2, they don't always have to be combustion. For instance, there's the luminol reaction. So iron within the blood will catalyze. So if I take a sample of blood and I put it with luminol and some hydrogen peroxide, then we can get sort of a light to show up. It's well, it's luminescent, right? So we're going to take peroxide. Peroxide will automatically decompose to water and oxygen. And then the oxygen itself can react with the luminol. And so the luminol then will produce a nitrogen gas, right? And so energy from that reaction will be released as light. And so we can see it coalesce. All right, so the appearance of the light would suggest then that blood is present. Okay, so that's how luminol works. All right, so the luminol reaction is initiated by the production of O2 via the reaction, peroxide going to water plus oxygen. What are the oxidation numbers of oxygen in the peroxide, water, and O2? So hopefully from the last segment you remember some of your oxidation rules. And so will it be -2 in all of them because oxygen's always a -2? And of course that can't be true, right? Because we know whenever we have something that's an element, it's got to be 0. All right. So they give us a hint here. They tell us the oxidation number of hydrogen is equal to +1 and takes the precedence over oxygen oxidation number. But of course, if you recall and look back at that previous segment, I told you that oxygen is always a -2 except in peroxides. And so here we have hydrogen peroxide. And so in hydrogen peroxide, we know that the oxygen should be a -1. Here, this is not a peroxide, so it's -2. And then here we have elemental oxygen, and so that should be a 0. And so of course our answer then has to be B, where it's -1, -2, 0 respectively. All right, so when we look at this luminol reaction, what is the reducing agent in the reaction and which compound gets oxidized? All right, so which one gets oxidized? So in this one we have oxygen as a 0. Here we have nitrogen as a 0. Here, since this is not a peroxide, we know these oxygens all have to be -2. So we kind of know who's getting reduced, right? Oxygen's going to get reduced, which means we know that the nitrogen then must be the one that's going to get oxidized. So that means we know if nitrogen's what has to get oxidized, and this is the source of nitrogen in the beginning, then we know that's got to be what's getting oxidized. And if that's what's oxidized, we know that's also the reducing agent. And so that's going to be A. All right. So reaction of metals with oxygen, and of course this is more or less corrosion or rust, if you want to think of it that way. The direct reaction of metals with O2. So many metals will corrode or tarnish, right? i.e. they'll rust when exposed to oxygen. So for instance, we did the magnesium reaction in lab, and I told you if you got one that looked kind of tarnished, you're going to have to rub it down with some steel wool. If not, you can find one that's really shiny. That's because that magnesium wire, that magnesium ribbon has been sitting out. It's been exposed to oxygen in the air, moisture in the air. That's going to be oxygen and the moisture, and boom, it just tarnishes, right? So aluminum can also tarnish. Iron, we know, turns to rust very readily. Silver, of course, tarnishes, and if you own any silverware, then, you know, maybe your parent, maybe you've had to, or grandparent will, you know, rub it down with a special little gel, and all of a sudden it's silver again, right? We call it polishing. You're going to polish the silver. What you're really doing is taking that level of tarnish off and showing the next layer of silver. All right, so aluminum metal and oxygen gas forms aluminum oxide solid. So here's our reaction. Solid sulfur burns an oxygen gas to make gaseous sulfur trioxide. So solid sulfur S8 burns in oxygen. So we're going to use O2 to make gaseous sulfur trioxide. So there's that one. Copper metal is heated in oxygen to form black copper 2 oxide solid. And there's that one. All right. Which of the following reactions is not a redox reaction? Which of the following reactions is not a redox reaction? All right, so basically what we want to do is look for those redox numbers, right? So whenever we see an element, we know that's a 0, that's a 0, that's a 0, that's a 0. None of these are elemental, which means none of these are zeros. On the product side, we can find the O2 is not over here. It's now reacted, which means it had to have either oxidized or reduced. Same thing here, right? We know that it had to have reacted somehow. And then we have the copper here has become the ion there. Strontium become the ion there, which means our answer has to be A. All right, so we're at the 22-minute mark. I really kind of want to knock this segment out though. And so the last thing we've got is stoichiometry and redox reactions. So pretty much this is not going to change any. It's like any other stoichiometry problem. The big difference is now you have to balance the redox reaction first. You'll then use stoichiometric coefficients to relate mole of one substance to moles of another. And so of course, it's going to look just like the other problems we've seen in previous chapters and segments. You'll start with the mass or volume of one reactant and find the mass or volume of a product. So now we might have some solution stuff we have to do. Or it might be formed in the wording might be a form of a titration. Okay, you might have to do limiting reagent calculations, stuff from chapter 3, test 1. And of course, we might have to calculate percent yields. So all of those things could still come back. So if you want to stop here, if you feel comfortable with those things, feel free. So these won't be new topics or new concepts. They'll just be now taking those old ideas and just relaying them and putting them in with redox reactions. So stoichiometry and redox reactions, how many grams of sodium sulfite are needed to completely react with this many grams of potassium dichromate? So again, the first thing you're going to need to do here is balance your equation, which means you're going to have to do your half reactions. Okay, once you get that, right, so after that, you're going to do the calculations like you would any other stoichiometry problem. So we'll go from mass of the potassium dichromate to moles, and then to moles of the chromate, the dichromate itself, right? Because that'll be the relation in our balanced reaction. And then we'll go from the moles of the dichromate to moles of the sulfate, and then moles of sulfate back to moles of sodium sulfate, and then to grams of sodium sulfate. So realistically, we're just adding a couple of steps because when we balance the redox reaction, it's going to be in terms of ions, not necessarily compounds, right? Because we'll ignore the sodiums, we'll ignore the potassiums, they're spectator ions, they're not doing anything anyway. But in order to take care of the mass piece, we have to add those in to the later calculations.
And thought, I'm thinking maybe we'll just go ahead and make another segment for the stoichiometry. I don't want to feel like I have to rush through it. I'm at 25 minutes. And so if you're comfortable with stoichiometry and you understand how you're just going to have these two extra steps in the middle, you can pretty much probably go through this on your own anyway. But if not, then I can slow it down and we can work our way through it. So stay tuned for the last segment for this chapter then.